Hi everyone, I am honored to stand before you today as we talk about extracting the electrical equivalence of a carbon nanotube and FET-based active bioelectrodes. My name is Mustafa Istanbullu and I am an assistant professor at the Çukurova University in Turkey. In this conference presentation, we will explore the concept of biological signals and the challenges faced with traditional electrodes. Furthermore, we will delve into the field of carbon nanotube field effect transistor-based biopotential electrodes, discussing their design, microfabrication, and the extraction of their circuit equivalents. To begin, let us address the fundamental question: what is a biological signal? In the realm of medicine and biology, a biological signal refers to an electrical impulse generated within the human body. These signals play a pivotal role in various physiological processes, enabling the transmission of information from one point to another. Understanding and analyzing these signals can provide invaluable insights into human health and pave the way for innovative medical diagnostics and treatments. Next, we will turn our attention to biopotential electrodes. Traditionally, these electrodes have been widely used to capture and measure biological signals. However, they have not been without their limitations. The problems associated with the traditional electrodes have motivated researchers to explore alternative solutions that can overcome these challenges and provide more accurate and reliable measurements. This brings us to the carbon nanotube and FET-based biopotential electrodes. Carbon nanotubes provide extraordinary electrical properties, making them ideal candidates for constructing highly sensitive electrodes. By utilizing the unique characteristics of carbon nanotubes and transistors, we can significantly improve the performance of biopotential electrodes, enabling enhanced signal detection and analysis. Throughout this presentation, we will delve into the design and microfabrication of MOSFETs, in other words, metal oxide semiconductor field effect transistors, in the context of carbon nanotube and FET-based biopotential electrodes. We will explore the techniques and processes involved in creating these advanced devices. Furthermore, we will delve into the extraction of the circuit equivalents of multi-volt carbon nanotubes, encompassing their resistance, inductance, and capacitance. By understanding the electrical properties of multi-volt carbon nanotubes, we can optimize the performance of carbon nanotube FET-based biopotential electrodes and unlock their full potential. Lastly, we will discuss the AC equivalent of the carbon nanotube and FET-based electrode, shedding light on its behavior in alternating current circuits. Understanding the AC characteristics of these electrodes is crucial for accurate signal acquisition and processing, as well as the development of advanced biomedical applications. Endogenic bioelectrical signals, also called electrophysiological signals, occur in nervous, muscular, and glandular tissues originated from electrochemical activities of excitable cells. Tissues of the human body act as a volume conductor, and related electrophysiological signals propagate through these tissues. Therefore, an electrophysiological signal can be measured by electrodes from the human skin surface. Tissue contacted electrodes are used in the bioimpedance and bioelectricity applications, such as observing electrophysiological signals, therapeutic impulse applications, transdermal drug delivery, and electrical property extraction of tissues. The instrumentation device is composed of electronic circuits and cables connected to electrodes. In the instrumentation device part, charge carriers are electrons, while the charge carriers in tissue part are ions. The electrode is a device that converts charge carriers from electrons into ions or vice versa. Ideally, an electrode skin contact should possess the low, of course, ideally zero, and stable electrode skin contact potential, and again, low and identical electrode skin impedance at two contacts. The electrophysiological signals captured on the skin surface contain important information about concerned organ functions, whether regular or pathological. In addition to the electrophysiological signals, there are also undesired signals due to noise, artifacts, and interface occurring in the orders of microvolts or millivolts. Briefly, a biological potential must be noise-free to be clinically valuable. Since undesired signals mainly appear by depending on the measuring electrode, the electrodes are crucial in terms of signal quality in a biological measurement system. In clinical applications, standard biopotential electrodes require the use of electrolytic gel and skin abrasion for better electrical interface between the electrode and the human skin. Since gel dries out over the time, signal deteriorations occurs on long duration recordings with these wet electrodes. Dry electrodes are a promising alternative for long duration recording, of course. However, they suffer from high contact impedance and they suffer from some motion artifacts. Electrodes made of many various materials with different arrangements can be found in the literature. Today, generally silver and silver chloride electrodes are the most widely used in clinical practice due to their low and stable half-cell potential, low noise level, non-polarity, and low metal electrolyte resistance. Of course, additionally, electrodes made of platinum, gold, and steel are also available in practice. While measuring electrophysiological signals from the body surface, the contact impedance between the electrodes and the skin surface also has a significant effect. The surface of the skin is abraded to reduce the impedance by cleaning the skin surface from dead cells, fats, and some hairs. These processes may cause pain and irritation maybe of the skin surface. Furthermore, in multiple electrode measurements, it's a time-consuming process to prepare the surface for each electrode. On the other hand, measurements taken from non-abraded surface suffer from high electrode skin impedance and motion artifacts, high power line interface, and some noise. In clinical applications, a conductive electrolytic gel is generally used for increasing the conductivity and contact surface area between the skin and the electrode. The conductive gel diffuses inward through the skin surface and it reduces the contact impedance. However, in long-term measurements, the gel dries out and the measurement quality of the signal decreases gradually. Allergic reactions on the human skin surface may also occur. On the other hand, the well-known electrical equivalent of the skin and a contacted wet electrode is given in the left-hand side figure. Please note that all the skin layers, electrolytic gel, electrodes, and each interfaces between them has a component on the circuit equivalent. Let's continue with a new type biopotential electrodes. Studies in the literature show that electrodes designed by carbon nanotubes usage in some proper sizes can easily reduce the high contact impedance and overcome problems encountered in electrophysiological signal acquisition. Here we have a novel active electrode with an increased contact surface by utilizing carbon nanotubes. The electrodes contains needle-like carbon nanotube arrays grown on and vertically aligned at the gate of an N-channel depletion type metal oxide field effect transistor. The vertically aligned carbon nanotubes penetrate the stratum corneum layer, that is the outermost layer of the human skin, which causes the noise. Therefore, bypass of stratum corneum eliminates the noise on the biopotential signal acquisition. The carbon nanotube array penetrated to the skin also provides a stable contact to the skin by increasing the, of course, surface area. Thereby, this supplies a low electrode skin interface impedance advantage for the electrodes. Since the electrode is attached more firmly to the skin surface, it prevents artifacts caused by breathing or limb movements. In the electrode model you see in this figure, carbon nanotubes pass over the stratum corneum, the outermost layer of the skin surface, which is composed of dead cells. Since each carbon nanotube is not sufficiently long to reach the nerve cells or living cells, pain and infection risk doesn't exist. So this approach has fewer penetrations into the skin surface than needle electrode models that work on similar principles. In this electrode model, since stratum corneum layer is bypassed by the employing carbon nanotubes, the use of electrolytic gel is no longer required. Therefore, undesirable effects such as the electrolytic gel resistance, gel stratum corneum interface potential, and stratum corneum impedance effects on measuring biopotentials are eliminated, and the equivalent circuit on the right-hand side is reduced to a much simpler circuit as shown in the left-hand side. The other important component of the electrode is the field effect transistor part. The MOSFET is fundamentally a three-terminal semiconductor device that the current flowing between the two terminals that is controlled by the third terminal voltage. As seen in the table, the maximum amplitudes of the signals are about, you see, 100 millivolts. The electrode presented here requires a MOSFET utilization to convert biopotentials to an amplified current form. The carbon nanotubes that capturing the biosignals from the skin surface are connected to gate of the MOSFET. Thus, the threshold of the MOSFET has to be low enough to be on state for all biopotential range, or the MOSFET has to be operate in saturation region continuously. For this reason, depletion type MOSFET is selected to fulfill these requirements, because the depletion type MOSFET has a built-in channel region, so it is continuously operates in on state. Therefore, if the drain terminal is positively charged with respect to the source terminal, the current flows through between source and drain, even if a positive voltage is not applied to the gate terminal. However, the channel depth, or we can say conductivity, can be altered by the applied voltage to the gate terminal. Increasing the gate voltage leads to an increase in the channel depth, thus results in an increase in also current flow. Consequently, voltage fluctuations on the gate terminal lead to fluctuations in current flowing through the source and drain terminals. Therefore, the biopotential is converted to current form in this way. The structural design and fabrication of the N-channel depletion type MOSFET in this electrode was simulated in a two-dimensional numerical semiconductor processing simulator. The flow chart of the microfabrication process is shown here, that starts with the N-type substrate selection and ends with open bonding pads. General microfabrication steps are written here, are epitaxial growth, thermal oxidation, dopant diffusion, ion implantation, photolithography, etching, and metallization processes. These itemized parameters like temperature, dopant type, or the others are the inputs of the each processes. And these figures show the structure of the depletion type MOSFET and its characteristic current and voltage curves under different operating voltages. Now, in order to extract the full circuit equivalent of the electrode, we need to extract the circuit parameters of carbon nanotubes. This figure shows the just simplified schematic of an individual carbon nanotubes. Here, the max is the diameter of outermost shell, while the dmin is the diameter of the innermost shell of the carbon nanotube. And the L is, of course, the length of carbon nanotube. During this modeling, resistance, inductance, and capacitance parameters are used to express the electrical characteristics of carbon nanotubes. Now, we need to talk a little about some nanoelectronic phenomena. The number of occupied subbands in a carbon nanotube by electrons making a contribution to conduction is dependent on the chirality of the carbon nanotubes. The probability of subbands being occupied by an electron can be represented by Fermi distribution function as stated by F function here, where the EI is the peak energy value for the subbands below the Fermi level as shown with EF. Then the number of conducting channels in any shell by considering the spin degeneracy can be acquired by adding up all the probabilities, and this is given by the N-shell function here. The ratio of diameters of the innermost shell to the outermost shell assumed to approximately 1/2. Thus, the number of shells P of the carbon nanotube can be determined by this first equation. If the shells from outer to inner are indexed as 1 to P, the diameter of ith shell is given by the second expression. Therefore, the total conducting channel number is the in carbon nanotube is the sum of conductive channels of all the shells. In the case of ballistic transport for a single wall carbon nanotube, the conductivity is independent of the carbon nanotube length, and it's determined by 2 times Q square over H times N, where the Q, H, and N are the electron. Q is an electron, H is Planck's constant, and N is the number of conducting channels in a nanotube. Then the conductivity of a multiple carbon nanotube in the case of ballistic transport is N times M times ballistic conductance times T, where the N is the number of shells, M is the number of modes, and T is the probability of an electron transmission in carbon nanotube. Experimental studies in the literature show that carbon nanotubes can exhibit ballistic transport up to several micrometers in length in some certain cases. The length of carbon nanotube designed in this study is about 100 micrometers. This length is much larger than the mean free length of the carbon nanotube, and the main reason for the resistance of carbon nanotube is the scattering originating from the acoustic phonons. The nanotube resistance for length exceeding the mean free path varies depending on its length, and the resistance is determined by H over 4Q squared times 1 plus L over Lm. But here, L is the length of the nanotube and Lm is the mean free path. Similarly, resistance of multi-volt carbon nanotube whose length is much longer than the mean free length is given by h over 2q square n times 1 plus L over m. Based on the literature, the total resistance of a metallic carbon nanotube can be divided into three parts as the quantum resistance, length-dependent resistance, and voltage-dependent resistance. On the other hand, at low voltages, the length-dependent resistance equations keep its validity to up to centimeter lengths. The related electrode that we're talking about is a biopotential electrode, of course, so that the electrophysiological signals with low amplitude voltages are applied to the carbon nanotubes on the electrode. As seen in the table, since the voltage range of biopotentials is between 5 microvolts and you see 100 millivolts, the low voltage excitation condition of carbon nanotube that stated in the previous slide is now provided. Therefore, under the low voltage excitation, the total resistance equation of the carbon nanotube can be simplified by neglecting the voltage dependent resistance. Then if we substitute the quantum and length dependent resistance values, we can get the intrinsic resistance of a shell as shown in the right hand side equation. The inductance of multi-volt carbon nanotube is similar to that of single-volt carbon nanotubes, composed of kinetic and magnetic inductance as well known in the literature. The kinetic inductance is 16 nanohenry per micrometer. Here, Q is the charge of an electron, H is again Planck's constant, and Vf is the Fermi velocity. Since the magnetic inductance is much smaller than the kinetic inductance, it has not been included in the multi-volt carbon nanotube model. The capacitance of multi-volt carbon nanotube consists of two parts as quantum capacitance and intershell capacitance. The quantum capacitance is a constant and it is approximately 100 attofarad per micrometer. Although the shell-to-shell capacitance can be defined by the right-hand side equation by using the coaxial capacitance formula, all the conducting shells in each multi-volt carbon nanotubes are connected to the same metal on the gate terminal of the MOSFET. The effective shell-to-shell capacitance is assumed to be bypassed in this electrode model here. A multi-volt carbon nanotubes consist of many concentric shells of different diameters. Thus, each shell has different mean free path and different circuit parameters. The resistance of carbon nanotube depends on the number of channels where the nanotube diameter specifies them. The mean free path also depends on the diameter of the carbon nanotube. Based on the analysis that we talked about up to now, the circuit equivalent of a shell is composed of quantum resistance, length-dependent resistance, and kinetic inductance connected in series manner. In this manner, the circuit equivalent of multi-volt carbon nanotube is composed of circuit equivalents of all the concentric shells in parallel, as shown here. On the other hand, since the carbon nanotubes grown on the gate terminal of the MOSFETs are vertically aligned and arranged in a parallel manner, the resistance of carbon nanotube forest can be expressed by R total over number of carbon nanotubes. Here, dimensions of the gate terminal of the electrode is 5 to 5 millimeters, and each carbon nanotube are grown with 50 micrometer successively spacing, so that the total number of carbon nanotubes for an electrode is approximately 10 power 4. Thus, the interface resistance of the carbon nanotubes are extremely reduced, in the overall electrode model. As it is stated before, the gate terminal of the N-channel depletion type MOSFET is covered with vertically aligned carbon nanotube array. Due to the depletion type transistor characteristics, the channel between the drain and source is conducting, and current flows even though there is no voltage at the gate terminal. When the electrode is attached to the skin surface, the carbon nanotubes at the gate terminal sense the biopotential signal, and oscillations of electrophysiological signals appear on the current flowing through the drain to source terminal. Here, the left-hand side figure shows the AC equivalent of the electrode containing both carbon nanotubes and the MOSFET transistor parts. By the way, this is the just equivalent of the 1 micro dimension electrodes, but here we have an electrode array, microelectrode array, as seen in the right-hand side figure. The drain and source terminals of the all transistors in this electrode model are electrically connected, as you see. Thereby, biopotential signals from different regions of the skin surface are accumulated. The measured electrophysiological signals on the gate terminal control the drain current. At low frequencies, for example, 1 to 5 Hz, for example, maybe, at low frequencies, the gate terminal of MOSFET, gate terminal of transistor exhibits an impedance that is too high to affect the measured biopotential signal. Additionally, the N-channel depletion type transistor provides direct current conversion and high dielectric insulation with skin and low noise pre-amplification of electrophysiological signals. These are some crucial advantages of this electrode model for instrumentation unit. I think this is my last slide. Thank you very much for listening to me. If you have any questions about the topic we mentioned here, please feel free to write to my email address on the first page of the presentation. Thank you.